Welcome to our presentation on the Quadfather drone project. I'm going to go and give a quick overview. So what we're doing basically is a 5-inch quadcopter with a carbon fiber frame. We're using carbon fiber because it's lightweight, robust to vibration, and resistant to fracture, because we're going to probably have a lot of crashes as we tune this thing. To control the actual drone, we're using STM32 because it's kind of an industry standard for this area. And it's basically going to take in an array of sensor data, then output a command to each of the 4 motors to correct for the motion of the drone. And the sensors that we're actually going to be inputting to the flight controller are a IMU barometer, ultrasonic rangefinder, and those will provide feedback and tell us how far we are from the desired state of the drone. In addition to the flight controller, the drone will also have an ESP32 camera board on it, which is going to stream video and send it to another ESP32 controller board, as you can see on the right. And that controller will take in the video data and put on the LCD the screen that you see here, and it's also going to transmit the controls from our joysticks and our thrust control so that we can change the motion of the drone however we may like. I'm going to go through a couple interviews that we had in guidance for this project. First is from Professor Freeman in the controls department, and the main takeaway that we got from him is that PID tuning will work well enough for our drone, and we don't need to go into nonlinear control or anything super complicated, because we're just interested in getting the drone to hover and fly around at a constant velocity, or like a controlled, pretty stable manner, and not doing all these crazy maneuvers that you would see from some racing drones. We're going to build a separate loop for pitch, yaw, roll, and thrust, and we're going to tune one axis at a time before testing the coupled motion. The coupled flight control will be slightly different, but having the parameters from each axis will be a good starting point. And then we can use the MATLAB control system toolbox to help simulate our responses and just input actual flight data that we have so we can have an easier time tuning it. And we're just going to prioritize a stable, controllable quadcopter as opposed to anything like a racing drone. And my second interview was from Kieran, who's a student in electrical engineering who worked on a project very similar to ours last quarter in 327. And he was just telling us to be prepared for potential fractures and potential issues with the drone braking as we're testing it. That's not really something we thought about, but it's kind of important to know that, like, when we tune it, it's going to crash. We might have to replace some parts, and we just have to be ready for that so that we can actually get the finished product working. And he agreed with Professor Freeman's approach on PID tuning, and he liked the idea of the STM32 flight controller. It's well suited for the stuff that we're working on now.
Here's where we stand in our design process. We've made a number of recent accomplishments. We've assembled a prototype with the drone frame, the 4-in-1 electronic speed controller, and the motors. And with this, we implemented a simple D-Shot motor control script using Arduino and varied motor speed via the serial monitor. We also built a tuning rig so that we can tune each axis one at a time. And to do this, we 3D printed a mount that goes on the bottom of the drone, which we can rotate 90 degrees to tune different axes. And our next steps are going to be to do this PID tuning so we can establish baseline parameters. We've also started the PCB assembly for the STM32 flight controller and power management board. We finished the assembly for the camera and receiver PCB, and we successfully ran the firmware for this wireless video streaming to the ground controller LCD screen. And our next steps are going to be to continue design of this ground controller PCB, which will include the screen, and continue developing the firmware for the communication that sends flight data between the flight controller, receiver, and the ground controller. Not much has changed in our overall design. One change we had to implement was our updated power architecture, which incorporates the buck converter on the flight controller PCB to step down the 14.8 battery voltage to 3.3 volts to supply it to the STM on the same PCB and the receiver on the other PCB. And we moved this buck converter from the receiver PCB to the flight controller because it simplified the ESC to receiver to flight controller wiring. Otherwise, there have been no major changes to our design.
So starting off, in the past few weeks, we've learned a lot about different communication protocols to drive motors and our ESC, which is our electronic speed controller. So there are different protocols such as PWM, pulse width modulation. We have also one shot, and there's a few others that we also tried. And these basically protocols communicate between the flight controller and the ESC, which actually feeds the analog, sorry, the alternating current for the motors that allows it to actually basically throttle up to a certain percentage and allows us to control it that way. And these different protocols are complicated sometimes, and not complicated, but we spent a lot of time debugging issues due to these protocols. For example, we were trying to drive our ESC with PWM when for some reason it only would work with one shot. So that was something that we ran into an issue about, and we were able to identify this issue and basically get it to work thanks to June and Charlie. They also helped debug a lot. But I spent, for example, a lot of time trying to debug this, and I couldn't fix it. But it was due to different protocols of the actual device. We also learned about reading the data sheets and using past designs. So, actually reading the data sheets, trying to find good, for example, PCB layouts or schematic layouts, and also just in general, making sure that our designs are correct and confirming that with past designs. So, for example, on our ESP, on our camera board, we didn't realize that we need a third voltage level for the actual camera, and we didn't realize that until we had to we checked the ESP cam, which is a breakout board of ESP32 with a camera on it, and they had the third level with a voltage regulator. So we realized we had to also include that. So that was part of our design as well. So if we didn't see that, for example, we would not be able to probably properly use the camera. Another choice or another thing that we've learned is buying components and backups. So always planning for the worst to making sure that when you buy components, you buy enough of them and you're not going to, basically regret your actions in the sense that there are times, for example, we ran into shipping issues where 4 weeks it took to get something like our motors, which are crucial for us to actually test and try to fly this thing. So that can be an issue, but we try to mitigate that by having backups. And then also protocol design. So this is an example. This is a code snippet that we have in our code that basically is the communication actual struct, I guess, that communicates that is sent between the controller, the handheld controller, and the actual receiver on the drone. And this allows us to control our actual drone without, just like in general, this is our control protocol. And we have different we have different parameters like throttle, yaw, pitch, roll, also an armed 1 bit to basically determine are the motors armed, can they spin or can they not spin, basically just for safety, and also a checksum to make sure that the actual bits that we're using weren't changed or corrupted. And then the questions that we had for the audios